really we are talking about molten salt reactors, and liquid fuel is really the key to that. It's the foundation for the advantages of molten salt reactors. Solid fuel, it's a complex challenge is the best way to put it. You make the slightest change to a solid fuel, change a spacer or a type of cladding, and you're looking at years of testing to make sure it functions properly. Irradiation damage limits the burn-up in solid fuel, and then decay heat removal. We can shut reactors down. Fukushima shut down, no problem. But it's the heat that's generated from all the radioactivity, we call that decay heat, that extends for days and weeks and months. Getting rid of that from solid fuel elements is the true challenge to making reactors safe, solid fuel reactors. Liquid fluoride fuel salts, though, the fuel is just unaffected by the radiation, very strong ionic bonds. That dramatically, of course, simplifies fuel qualification. The fuel is the coolant, and that just in many, many ways, it's a bit, there's a lot of tangents we could go on here, but it really simplifies decay heat removal because your heat source is mobile. And you're operating at low pressure with very, very high boiling points. So there was a lot of liquid fuel reactors looked at in the 50s and 60s, but really only these fluoride salts proved practical. Advantages, I'll only have one page here. We could probably do 10 or 20, but safety, it's that inherent safety, that passive decay removal, the fact that the liquids can naturally circulate so that they can be moved to other areas to deal with them, or within the reactor itself can naturally circulate to move the heat around. They're operating, like we said, at low pressure, and there's no chemical driving force within the reactor. There's nothing that could generate hydrogen like water, zirconium interactions. Just in a sense, nothing pushing its way out, which is a very good starting point. And very important in any solid fuel reactor accident are cesium and iodine. They're both volatile, so the many years of production are in that fuel pin just waiting to get out. With the molten salt reactors, cesium becomes a cesium fluoride, it's stable within the salt, and iodine becomes a form of iodide, and again, it's reasonably stable within the fuel salt, and that gives us great safety advantage. Reduced capital cost and inherent safety can really simplify the entire facility. So all these things, including the low pressure operations, so thin-walled vessels, thin-walled piping, very high thermal efficiency compared to existing reactors, superior coolants in general. We need smaller pipes, smaller heat exchangers than current reactors, and very important, no complex refueling mechanisms. And that's, I'm Canadian, our CANDU reactors are great, but my God, the complexity of the refueling operations there. Long-lived waste issues, and they're an ideal system for consuming existing transuranic wastes. In spent fuel, it's really plutonium and the other ones, americium, neptunium, that's the problem. In spent fuel, 96% of it is relatively harmless, unused uranium. That's not really anyone's problem. There's 3% that are fission products, but that's a quite manageable problem because they're not as long-lived as the transuranics, which is only 1%. But many reactors, molten salt reactors included, can take that transuranics and turn them into useful energy. When we talk about the waste we do produce, even burner designs, and I'm going to go back and forth between this idea of burner and breeder, but even the burner designs can see almost no transuranics going to waste. And then resource sustainability and low fuel cycle cost. Thorium breeders, the IMSR breeders, it's obvious resource sustainability for millions of years, but even the burners they're extremely efficient on uranium, roughly 1/6 the needs of light water reactors if you choose the burner route. Quickly on the US historic timeline, first envisioned in the late 40s. In the 50s, they became a leading candidate for a quite well-funded aircraft reactor program. The Navy gave birth to the light water reactor. The Air Force, in a sense, gave birth to the molten salt reactor. Huge knowledge base developed, and a successful aircraft reactor experiment test reactor operated in 1954 at what still might be the highest temperature of a reactor, 860 degrees, just meant as a short-term test. That evolved in the 1960s and 70s into the MSBR molten salt breeder reactor, or what you'd call the Thorium Breeder. At the time, world thinking was there was very little uranium in the world. We found a lot through extensive efforts during the war. But back then, people thought, well, we need breeders by the 1980s. So it's going to be either sodium fast breeders, or the alternate technology was the molten salt breeder, the Thorium Breeder. So that really started to dominate research efforts in the United States. And the molten salt breeder reactor program had a very successful 8 megawatt thermal molten salt reactor experiment in the mid 1960s to late. Some minor issues uncovered, but very, very successful reactor. 70s though, falling of the political axe, the program was canceled in the mid 70s, and we won't get into all the different reasons, and there was a lot of different reasons. Some fascinating work continued at Oak Ridge, that's where the work was being developed for molten salt reactors, on a burner design called the DMSR, and I'll get back to that a little bit later. So that's a picture of the molten salt reactor experiment that many of you have seen many times. Just in a sense, a simple tank, graphite as the moderator, so you just have rods of graphite with spaces in between for the fuel salt to flow. In this case, a simple pot and a pipe leading out to a heat exchanger externally. This is from what we call the Gen 4 program, a world collaboration of what are the best advanced reactors to work on for the future. Molten salt reactors were chosen as one of 6 Gen 4 reactors. This is from their program guide. This is really the 1970s version, graphite moderated on-site chemical processing, so you can be a breeder. You have to pull fission products out rather quickly to be able to be a breeder reactor. The freeze plug, which you've heard about before, dump tanks to deal with the decay heat. I think others will go into this as well, so I won't say too much. The only change in the Gen 4 being 2002, helium Brayton cycles were kind of all the rage. Most of my colleagues that we're talking about these are maybe back to steam now, or CO2 is interesting as well. But that's not what I'm going to be talking about, but that's what you'd probably call the textbook reactor. Summary of current world events, as I've chosen as one of 6 Gen 4 designs. Widespread grassroots support, which has definite pros, can have cons as well. The funded US efforts, a lot of my colleagues at Oak Ridge and elsewhere, they're looking at a cousin technology, which is traditional solid fuels, not like light water reactors, but graphite-based reactors, but replacing helium coolant with molten salt, so the same FLIBE salts as a replacement for helium. And there's a lot of advantages of that, but really when you really look at things, it lacks a lot of the major potential benefits that true molten salt reactors have. European efforts are focused on a fast spectrum version, getting rid of graphite. That's an admirable goal. It gives you many advantages, but a lot of challenges in that route, and even they are looking at quite a long development horizon. China, as you've already heard, really has led, I wouldn't say led the way, but really changed the playing field by their program, roughly a $500 million program, looking to build both a salt-cooled reactor first and quickly followed on by that of a true molten salt fueled reactor. Quite like the first demonstration of the MSRE. India keeping options open. We had a very interesting conference there a couple of years ago. They had a lot of efforts going in the 1970s that many of us weren't aware of. And as you've heard and will hear, several startup firms worldwide. So why the renewed interest? Light water reactors have served the world well, but there's really only incremental improvements possible. Going to small modular reactors with light water, that's definitely some benefits there. But nothing that's going to be a true game changer. And it's the passive safety of molten salt reactors that really opens the possibility of true cost innovation. And that's really needed if we are going to build these by the hundreds and thousands. Molten salt reactors open up the possibility of reducing the nuclear waste profile and the ability to consume existing waste. They can be configured as factory fabricated small modular reactors. And when you're talking about, well, modern molten salt reactors, it's quite logical to first look to the past. Now I'm going to get quite technical here, and those that you can understand probably have heard me talk about this already, so I'll zip through this so you can ask me questions later, but a lot of challenges for that textbook design from the 1970s. On-line fission product removal, do not estimate the difficulty of that. Much simpler than processing solid fuels. but still a great challenge. Tritium control, molten salt reactors using enriched lithium and beryllium as their carrier salt will produce a fair amount of tritium, and stopping tritium has this annoying habit of going right through hot metal walls. So tritium control was always a big part of early work. Reactivity coefficients, again, how you always want the reactor to power down if the temperature gets hotter. They were the needed negative term, but only calculated to be quite weakly negative. The use of highly enriched uranium, which I don't really want to get into too much, but that word alone and a thorium breeder by definition involves that. As soon as you say those three words, you're going to get a lot of doors closed in your face. Off-gas handling, we talked a little bit about xenon and krypton coming out, and those can have daughter products that we have to keep an eye on. So that is a challenge. Noble metal fission products tend to plate out on surfaces. That can give you a challenge, nothing insurmountable, of course. And then long-term corrosion and radiation damage. Oak Ridge developed very good materials for these, a lot of testing, but proving that for 50, 60 years of current reactors is a challenge. And then if you're using graphite, if you want to talk about replacing graphite, that is maybe harder than you think. So why graphite? If you're looking at, well, what should a modern one, why should we use graphite? Because it does indeed present challenges. There's disposal issues. That varies greatly when we're finished with the graphite as a moderator. It will be modestly radioactive. Chlorine-36 is something that can be involved, so it varies greatly by regions. Depending on regulations for that. It's largely a perception issue. There's not much radiation involved here, but still of importance. It does add, theoretically, a chemical potential, but in fact, it's almost no added safety concerns. There's something called Wigner energy, which some of you might have heard of. That was the cause to start the wind scale fire in the UK, but that's not an issue at higher temperature reactors like molten salt reactors. Graphite is near impossible to burn. The wind scale fire was not graphite burning, it was the metallic uranium and metallic aluminum cladding that was really burning. And Chernobyl was, well, it was a mess of a design to begin with, but that was basically a nice furnace that had, everything was blown apart, air blowing through, and 2,000 degree plus molten corium, the molten form of the solid fuel, driving reactions there. Why graphite? It does give you many large advantages. It's the only unclad moderator that's possible to use with the molten salts. Graphite enables, you can protect all your structural materials, all the metallic structures, etc., from high neutron fluence by a method we call the under-moderated outer zones. You can't do that with the fast spectrum reactors. More thermal spectrum aids the reactor control things. It just slows things down in general, long neutron lifetimes. Makes your power truly scalable from large to very small. Massive reduction in the needed fissile material to start the reactors. And if we're using low enriched uranium as your fuel salt, it's a surprisingly low, theoretically down to about 1%, probably 2 to 4% is a more practical region. So why a thorium breeder? Thorium breeder, it is a very admirable goal, and groups like this should continue the effort. It's a very simple message to the public. It will give us potentially millions of years of resource. But the breeder approach does represent many unique challenges, especially on-line fuel reprocessing. And that, unfortunately, will lengthen development time. And long development times mean private funding is extremely hard. Governments will not lead any more nuclear development, but they will follow. They will follow private capital. So we know now that uranium is quite abundant. Yes, if you look at the Red Book, it says there's only 80 years at current use, but if you look how much, there's probably 30 years of copper. If we need more, the price might rise a little bit, but then there's more lower grade ores. So there's a lot of uranium out there. So do we need to go straight to a breeder? Because an MSR burner, which you know I'm going to be pitching here, that can simply use low enriched uranium as the fuel, as the makeup fuel and the startup fuel, and use it much, much more efficiently than current light water reactors. The MSR burner approach immediately removes many of the big challenges from the breeder approach to greatly simplify things and shorten your development period. The last major work of Oak Ridge was on a burner design, the denatured molten salt reactor, which I'll talk very briefly about here. They called it the 30-year once-through design. So you're using the same salt. You start up with low enriched uranium, trickle in a little bit more low enriched uranium every year. Originally mandated to increase anti-proliferation features. So you're starting with the legal limit of low enriched uranium, 20%, only to be able to put in as much thorium as possible. I view in this case thorium, it's like a fuel additive. It makes your fuel economy better. I'll get back to the pros and cons of thorium or not. There's no salt processing, just add small amounts of low enriched uranium. A low power density core gave a full 30-year lifetime out of the reactor, but that made it quite big, 8 by 8 meter core and about a 10 by 10 meter reactor vessel. Similar fizzle starting to a light water reactor. Uranium needs, depending on whether you look to recycle the uranium at the end of the 30 years, was either 1/6 or 1/4 of the uranium needs, only about 1/10 of a cent a kilowatt hour for fuel costs. And that's modern day numbers. About 1/9 of the transuranic waste and that's assuming you didn't do anything with the plutonium except put the salt to geological storage. Much better reactivity coefficients than the breeder. The breeder was calculated to be just slightly negative. A French reworking of things, we're worried it might actually be slightly positive, but the burner approach was a nice strong negative. And it's really cool reactor physics of why that is the case if you want to pester me later. I want to kind of debunk some burner myths because these aren't thorium breeders and some will raise problems. And I hear this, if it's not a breeder, it's not sustainable. Well, but when you really look, the burners are extremely efficient on low enriched uranium. So you theoretically could replace every light water reactor, coal and gas plant with burners and see little, if any, need to increase current uranium mining. And current uranium mining is a drop in the bucket compared to other mining. We won't have millions of years worth like thorium, but easily thousands, is even if you allowed the price of uranium to rise tenfold, it's just an enormous potential reservoir of uranium. The other myth, I would say is a myth, is the MSR burner means you're making plutonium waste, therefore it solves nothing. The burners produce a lot less PU waste because, I won't get into the physics, but we burn up so much of it right in the reactor if we're running them this way. And we have the ability, after a long period of time, we can do this a decade later, we can recycle the plutonium and all the rest, americium, neptunium, and just put it in other fuel sources. So we have the same ability as MSR breeders or the sodium fast breeders to close the fuel cycle. So you're really only having fission products and maybe some relatively harmless unused uranium as your waste. But that's a nation's choice. If a nation wants to go right to the once through cycle, there's a lot of real solutions now. Salt caverns are an excellent place to put spent fuel if we ever choose to do that way. Another one is MS burners require uranium enrichment. And I will concede that point, that yes, but if we're running the world using burner type reactors, because we do it so much more efficiently already, we need so much less enrichment, we don't really need to increase the current enrichment facilities. And you're not going to really uninvent a technology. I won't really, anyway, just quick mention, there's an interesting synergy with CANDU reactors that use natural uranium. They're actually quite good producers of plutonium, and we could use that as a fuel source for burner reactors. So you could have a fleet expansion without enrichment. Issues solved just by going to the burner approach. Fission product removal, we don't have any need for on-site processing. We may choose to process the salt once we're finished it, but like I say, that's a nation's choice. Tritium control, we're not giving up on enriched lithium or beryllium, but when you're not a breeder, not trying to save every last neutron, we have the ability to use non-flied carrier salts that really knock down the tritium production by about 99%. Reactivity coefficients, the burner designs it's really between uranium-233 and plutonium and uranium-235, just far superior reactivity coefficients. Off-gas management, we don't have to pull the gases out really, really quickly like you want to do with a breeder design, but it just gives us more options, which again, I won't go into too many details. Highly enriched uranium use, we're not using that. The uranium is always denatured. Any PU present really quickly builds up to a lot of 240 and a lot of 242. Both those make it virtually, if not literally, impossible to use in weapons. The remaining challenge I'd say are really materials related. Noble metals tend to plate out in heat exchangers. We always knew you're not going to talk about going in and fixing a heat exchanger. If you have a problem, you're replacing the entire tube bundle. A little tricky if they dry out, if there's a heat source there. Long-term corrosion and radiation damage of the metals we use, high nickel alloys, Hastelloyen, even some stainless steels perform superbly, but proving a 30 to 60 year lifetime is going to be a challenge to the regulator, to the investor, etc. Graphite replacement, it gives you very strong advantages, but its lifetime is limited by the power density. And if you want to change it, so this led to a very long, for decades with Oak Ridge, this seal or swap. So you have a limited lifetime if you use it at a high power density. So do you seal the reactor for the lifetime with a low power density, or do you go to a more economically viable high power density and then plan to replace graphite? So early work, yeah, let's make them smaller and we'll just replace the graphite every 4 years, but that is far more difficult than many might imagine. Later work at Oak Ridge said, no, let's go to low power density, very large cores, but then higher capital costs. There's more fuel salt, bigger building, all that. So what is our integral molten salt reactor? As you would have guessed, of course, the idea is a burner design, a lot like the 1980s DMSR. We want to integrate our primary systems into a sealed reactor vessel, planned in a variety of sizes from 80 megawatts thermal up to 600 megawatts thermal, using off-the-shelf steam turbine technology. Maybe in the future it'll be CO2 or helium, but we feel initially it's steam. Small modular factory fabrication is allowed. We have the ability to look at alternate salts and new off-gas systems. And a new passive decay removal. We prefer in situ, not really going with dump tanks. We won't really get into it, except I'll just show you what we're up to. In thorium use, we have not yet decided. We haven't ruled it out or ruled it in. There's actually a remarkably long list of pros and cons whether we use thorium. And in a burner design, it's really thorium is just replacing uranium-238 as a better fertile. So we'll either use it and use more 19.9 or 10% enriched uranium, or if we don't use thorium, then we go to really low enrichments in the fuel. We have what we call a seal and swap approach, so the many technical challenges are addressed in our technology. Simply stated, our primary vessel is meant to be a perfect, permanently sealed system, of course pipes going in and out for coolant salt, etc., with an economically high power density, much less than a 30-year lifetime. So after a 7-year design life, an identical IMSR core unit replaces the old unit for an indefinitely long plant lifetime. We build in redundancy on our heat exchangers, so if we have a failure of one, we can continue with the remaining, and to continue its quite limited lifetime of 70 years. So basically sealed for life plus replaceable is what we're talking about. So the core unit, I won't get into too much details, and quite obviously we're not always showing every last little bit, or maybe even misdirecting in a sense. I also tend to call this the 2014 version. We had a deliverable of a preconceptual design report. We had to make the most conservative choices we can. We are now into a stage, our second phase of development, where we can make some changes. So there has been changes, which of course I won't tell you about. But the basic idea is graphite in the bottom of the reactor vessel. These sort of orange wedges, 6 of them, 3 shown, are the heat exchangers, each separately. And each heat exchanger has a pump motor. You can't see the impeller, but it would be just inside there. Very simple impellers because it's very low pressure drops, very low power. That's only 10 kilowatt pump for the smallest unit. Each has its own inlet and outlet for secondary coolant salt. So a secondary coolant salt is taking the heat away from the reactor, but the fuel salt, everything radioactive, is staying in there. Off gas, we have a lot of options, which I won't get into. But fuel salts push through the heat exchangers, down through the annulus, up through the core, up through a chimney, and then repeats that cycle. And up in here, that's a big gas plenum space, so we can pressure changes, volume changes as we feed in more fuel, etc. We're showing a flow-driven shutdown rod. If the pump stops, that rod will drop by gravity, and an independent secondary shutdown system of a neutron absorber injection, which is thermally based. That goes within sort of the next layer of containment. We have what we call a buffer salt liner, which I'll talk more about, but this is a big, thick, roughly about 1 meter thick of just pure, simple salts, fluoride salts. A nice cap here that we can remove to exchange the unit. Showing the next level, then we start to get into like thick concrete, nuclear grade concrete for all kinds of, to make sure you drop down radiation levels to next to nothing. Big steel plates that are not shown that can be removed when we have to remove this replaceable core unit. The facility itself could be, of course, multi-unit plants. We typically always show 2 silos though. These are identical. So the operation principle is the first unit arrives. By the smallest unit can likely, we're kind of pushing weight restrictions, but the smallest unit can be completely factory fabricated. The larger units, just by weight issues, might have to come in pieces where we put them together in here. The first unit is installed and that will run for 7 years with this other silo just empty. When that 7-year period is up, or just before, the second unit can come in, which is installed into the second silo. So when we shut down that first unit, we don't have to do anything with it quickly. We have a full 7 years for it to die down, the radiation levels. We don't want to touch it for a while. The fuel salt, it's liquid, it can be taken out at any time. But we have 7 years while the second unit operates. Then just before the third unit, that's when we can drain all the fuel salt, lift it out and out to long-term storage silos. And it's quite low levels of radiation by then. Sort of a bit of a peer comparison, other small modular reactors. This is not apples to apples comparison, but just kind of shows the size of units that need to be shipped. This is meant to be our largest unit, 3.6 meters wide, roughly about 12 meters tall. Compared to the new scale, their 50 megawatt electrical unit or 160 megawatts thermal. M-Power, unfortunately, isn't really, it's a bit on the shelf. By the end, they were at a bit of a higher power level, but it just kind of shows a comparison of size. This shows between our different core unit sizes down to the 80 megawatt thermal. And this is with the most conservative choices, the most conservative heat exchangers. So in the future, these sizes can be improved or reduced. A bit of a comparison with a small light water reactor, the AP600, that hasn't been built and they went right to the larger, and with our largest unit, so it's more power with the AP600, but just showing like you almost need magnifying glasses for a lot of the components, whereas the 70-foot tall steam generators and everything, foot thick steel, etc. Gives you an idea. The other thing as well that light water reactors can do is they have big, wet steam turbines. The steam conditions we're looking at are identical to coal-fired plants, so either superheat or supercritical steam, very compact units. But challenges solved with the IMSR, that sealed for life offers enormous regulatory advantages to accelerate development. The spent vessel is now, it's repurposed to be a storage of the mildly radioactive graphite. We don't have to worry about airborne release if we're looking at swapping graphite or heat exchangers, etc. We have a long cool down time before moving. Material lifetime and corrosion, anything that's touching those radioactive salts, we really only have to prove a 7-year lifetime. And it allows evolution of design with ease, and maybe not as obvious, but there's a razor blade analogy here to attract potential business partners. They know that it's not just how many reactors you build, but if we build these, there's business for decades and decades on replacement core units. Very quickly on our concepts of decay removal, and again, in the future things may be slightly different, but that buffer salt is meant to be a solid during normal operation, which is also a good insulator. Any solid can be. So by the time you're getting out to concrete, that has really shielded amount of heat that's transferred. But if we lose all pumps, this salt is chosen to be at a melting point just a little higher than normal operation. So if all the pumps stop, and of course you'd always have natural circulation to steam, but if we assume there's absolutely no other heat removal, then the buffer salt starts to melt. That draws heat away from the reactor. And of course, if the salt is the coldest on the outer edge of the reactor and hottest inside, that's going to set up natural circulation. And we get a couple days in the smallest unit before all the salt, or almost all the buffer salt, is melted. And then a water jacket that's protecting the concrete from ever getting too hot. That can take over sort of the heavy lifting for very long term. And there's a lot of reasons. You can look at radiant heat straight up. These are completely walk-away safe. but there's a lot of engineering work to prove that to the regulatory body's satisfaction. So the bottom line, we deliver hot, clean salt that can be used directly for process heat. We can add a steam generator for process steam, and the most, obvious use is adding a turbine generator for power. We feel it's the simple approach, easiest to achieve regulatory license and public acceptance. Cost innovation is the end result. The fuel costs are almost trivial, less than a couple tenths a kilowatt hour. That's including enrichment, everything. Our early cost estimate work was at $2 a watt electrical or 60 cents a watt thermal for the largest unit. For the smallest unit, at about 32.5 megawatts electrical, about $5 a watt. Economies of scale when you try to shrink them. Our Canadian government would love us to go even smaller, but we kind of resist going any smaller. So our phase one, we've had detailed cost engineering work has added to confidence. Our phase two work will expand this enormously. So design simplicity is the key, but of course much work ahead, pump development, salt selection and validation, heat exchanger design, the nitty gritty of things, valve and disconnect systems, steam generation. All quite solvable issues, but it's just some good old-fashioned engineering to do. Quickly, a bit of a business update. So we were founded in January 2013, but most of us has been involved for this many years before that. I met Simon Irish at one of these conferences. I forget if it was the second or third, but this really brings people together. So the directors of our company and myself as Chief Technology Officer, I'm not sure if Simon has arrived yet. He'll be here sometime today. Simon Irish, our CEO, has been very, very excellently guiding our corporate ship through sometimes, of course, shark-infested waters, doing an excellent job. Cannon Bryan, our CFO, which I think is here somewhere in the room, or if not, wheeling and dealing out in the hallways. Hugh McDermott is chair of our board, and Dave Hill, a fifth director. I'll mention those fellows more. We are, of course, building proprietary molten salt reactor technology. We hope to have the first commercial unit, demonstration unit in early next decade. Our team consists of over 28 directors, employees, consultants, and advisors. I mentioned some of the main sort of management team, Paul McIntosh, who is, Paul's here in the room, Rob Bodner, Cyril Rodenberg, Mike Edwards, I'll mention him again later, Brian Mercer, Chris Popoff, the main team, but we're rapidly expanding. We've completed phase one, all our seed financing, our deliverables of the preconceptual design, formed our management team, formed the company to grow into the larger company that we are now becoming. Quickly on milestones, I won't read off some early milestones. Dave Hill was senior executive management positions at both Argonne, Oak Ridge, and Idaho National Lab on our board. Hugh McDermott, former CEO and president of Atomic Energy of Canada, very early adopter, so to speak, has been incredibly helpful for us and very, very involved. Completed our seed financing, filed patent in 59 countries, completed the preconceptual design report in all its glory in the fall. Public launch in September, entered agreements with Canadian Nuclear Laboratories, that's up in Canada. Initial collaborations with Oak Ridge that are, first stages are complete, we want to do more, and University of Tennessee. Very lately, this isn't very update, but Jeff Merrifield, former NRC commissioner, Mike Edwards, on our advisory board, but transitioning to being a full-time employee. I'm not sure if that's official yet or not. If it is, it's only been a day or two. The senior design engineer of the mPower at Babcock & Wilcox. He's been enormously helpful to date. Paul Blanchard, James Reinsch, former CEO of Bechtel Nuclear, joined the advisory board. And let's just say, stay tuned for details. If this was a few weeks from now, I'd have a lot more interesting things to announce potentially, but I can't really say about them. But that ties into what I consider our biggest surprise. Things have been going quite well, but I think our biggest surprise is our reception within the existing nuclear community. We kind of expected indifference from light water folks or fast breeders. That has not been the case. This is, blatant self-promotion here, but a good example of that is Nuclear News, the American Nuclear Society publication. They chose the 10 advanced reactors in the world, of course with a US or North American bias, but we're chosen as one of those, and that was only about 2 months after we, in a sense, came out publicly. And like I say, just a lot of people are coming to us, and it's been an amazing experience to go through. So phase 2 development in this year and next year into early 2017. We're expanding our team. more strategic technical partners. Again, like I say, if it was a few weeks, we'd probably have more announcements we could make. More national lab work in North America and Europe. Goal in this second phase is to really complete 3 files that will help us secure the major funding to actually get the reactor built. So the design specified to the conceptual design standard, ready to go then to the engineering blueprint stage. Licensing, we want to go through the first phase of the vendor design review in Canada by the end of this 2-year period to finish it. That gives you a report card, initial report card. And economics really proving out, there's a lot of money involved to proving these early cost estimates. So just kind of ending up here, we feel this is a new paradigm for nuclear energy, a new economic proposition of being cost competitive. We feel we will be extremely competitive with coal and even cheap current natural gas, scalable, it's a global energy resource to rival fossil fuels, accessible heat and electrical energy, secure, reliable, portable, grid-independent energy. These can be built and established either as traditional grid units or in more remote users. And we feel it's a new social proposition as well, that passive safety. It's a completely different narrative to the current nuclear safety. Nuclear power today is safe, but it has cost them a lot to be that safe, and it's a very hard message to get across to the public. But with new technology and with passive systems, that should be a much better narrative. For a smaller and more manageable waste footprint, the possibility of virtually no long-term nuclear waste. The burners do not need to process during use. It's probably going to be the case, and most users will choose to then reprocess, take all the plutonium, americium, put it in another fuel source, and it gives you an amazing long-term waste profile. And just exemplary proliferation resistance. That's why the denatured molten salt reactor was developed in the first place. So we really feel it has the potential to change the game in energy production. So we often throw contact details. This is going to change very soon. People are still signing. We're moving into new office space. We're very happy about signing the lease today. So lots happening. The story is different every week.
How does your use of graphite moderator compare with Transatomic's proposed use of lithium hydride as a pilot moderator in the reactor?
Yeah, the question was how the use of graphite compares with Transatomic's ideas of using zirconium hydride as a moderator. It's a quite different situation. Graphite it can be used without cladding. The zirconium hydride has to be clad with something. So I won't say too much. They have a lot of challenges to go through. It's a more compact moderator, but you go to any nuclear engineering textbook, if you list out moderators, hydrogen doesn't typically pass graphite. Heavy water does, but I don't want to have heavy water or water as moderator, of course.
How was your company funded from start, conception to today? How did the funding mechanisms work?
I always have to hesitate because, of course, it's a private company. I can't stand up here and say there's a lot of things you can't say. But let's just say it's gone very well. It has been completely private investors, not a government, sent from government. Not that we wouldn't take it and not that we're actively seeking it, but it has been entirely private investors to date.
I think that's about it. Let's give Dr. LeBlanc a hand. Thanks, Dave.
Yep.